Welcome to Section 10, Lesson 7. Solving radical equations means finding x values that make a radical containing equation true. The procedure is straightforward, but the check step at the end is non-optional because raising both sides to a power can introduce false solutions. The procedure has 4 steps. Isolate the radical on one side, raise both sides to the radical's index. Solve the resulting polynomial equation. Check every candidate in the original equation, reject any that does not satisfy it. The check step exists because squaring is not reversible. If a equals minus b, squaring gives a squared equals b squared, which is also true when a equals plus b. So squaring can produce extra candidate solutions that were never solutions of the original. Cube roots and odd index roots do not introduce extraneous solutions because cubing preserves sign. Even index roots like square roots and fourth roots do, so the check is essential when the index is even. Take the square root of x plus 3 equals 5. The radical is already isolated, so we move directly to squaring. Square both sides. The square root and the square cancel on the left, leaving x plus 3. The right side becomes 25. Solve the linear equation x plus 3 equals 25 gives x equals 22. Check. Substitute x equals 22 into the original. Square root of 25 equals 5, exactly matching the right side. The candidate checks out, so the answer is x equals 22. Example 1. Solve the square root of x plus 7 equals x minus 5. Squaring both sides will produce a quadratic, and we may end up with 2 candidates. Square left becomes x plus 7. The right becomes x minus 5 squared, which expands to x squared minus 10x plus 25. So x plus 7 equals x squared minus 10x plus 25. Move everything to one side. X squared minus 11x plus 18 equals 0. Factor this is x minus 9 times x minus 2. 2 candidate solutions, x equals 9 and x equals 2. Check both. At x equals 9, square root of 16 is 4, and 9 minus 5 is 4. The two sides agree, so x equals 9 is valid. At x equals 2, square root of 9 is 3, but 2 minus 5 is negative 3. 3 does not equal negative 3, so x equals 2 is extraneous and gets rejected. Example 2. Solve the cube root of 2x plus 1 equals 3. Cube roots are odd index radicals, so the procedure is the same, but no extraneous solutions can sneak in. Cube both sides. The cube root and the cube cancel on the left, leaving 2x plus 1. The right side becomes 27. Solve. 2x equals 26 gives x equals 13. Check. Substitute x equals 13 into the original. Cube root of 27 is 3, exactly matching the right side. The check passes. The cube root case is cleaner because cubing preserves sign and produces no false candidates. 3 takeaways for solving radical equations. The third one is non-negotiable. Isolate the radical first. If there are constants or other terms on the same side as the radical, move them away. Once the radical sits alone, raising both sides to its index cleanly removes it. Solve the polynomial equation that results. After raising to the index, the radical disappears and you have a polynomial in x. Use whichever technique fits linear isolation, factoring, the quadratic formula, or others from earlier sections. Always check candidates in the original equation. Squaring and other even power operations can introduce false solutions. Cube roots and odd index roots do not, but checking is still good practice. Reject any candidate that does not satisfy the original.